This is Unit 1, Relations and Functions, Section 2, Logarithmic Functions, which you'll find in Chapter 7 of your textbook. At the conclusion of this chapter, you will be able to develop algebraic and graphical reasoning through the study of relations, demonstrate an understanding of logarithms and the laws of logarithms, and represent data using logarithmic functions to solve problems. A logarithmic function takes the form y equals log base b of x, where b represents the base of the logarithm. Logarithmic functions can also represent a large number of natural phenomena and human activities, such as pH, decibel level, and Richter scale. Many of the examples will demonstrate logarithmic growth and decay in these instances. Logarithms were used in the days before calculators were developed in order to simplify complex calculations. The following sections will show the relationship between exponential and logarithmic functions. These are the requirements to show mastery for this section. Part 1, Characteristics of common or natural logarithms, notes and practice, as will be seen in every one of the parts. Part 2, Evaluating logarithmic expressions. Part 3, Laws of logs. 4, Solving exponential functions using logarithms. And Part 5, Modeling data with logarithmic functions. To complete the section, you will have one formative assessment, the logarithmic functions review, as well as 3 summative assessments, those being the curriculum review, the quiz, and the exponents and logarithms section exam, which of course is a final summative assessment on chapters 6 and 7. Let's get started. Part 1, Characteristics of common and natural logarithmic functions. Logarithmic functions are produced by graphing y equals log base b of x. Like exponents, the base b has restrictions. However, this section focuses on the graphs of functions where b is 10 or e. We'll start with the base 10 logarithm. The base 10 was the original logarithm, or y equals log base 10 of x, due to our decimal or counting system. Remember, of course, 10 fingers, 10 toes. We use base 10 for most of our counting. So that's why they decided to start with logs in the form of base 10. As such, it is often written as y equals log x, where there's no base 10. This is known as the common logarithm. Construct a graph of y equals log x on the grid below and fill in the table regarding its characteristics. So, as you can see, I've already labeled a couple of points on our graph. Please make sure that you try this on your calculator, so look and see where your log button is, okay? And then it's probably, you'll have to press some second and then 10 to the x. Okay? So that's the kind of thing you're going to have to worry about seeing. All right. Now, if we were to graph that, so again, if you want to pause the video and graph on your calculator, and then come back and see what I'm doing here. Alright, so we know that the graph goes through the x-axis at 1, and we also know that, and I'm going to just make the, every one of these, every 2 spaces, make them 1. Okay? So if we go to graph this, we know it goes through the point here, 1, 0, and I know that log 10 is 1. Okay, so that's a 1, that's a 2, that's a 3. Okay, so my graph goes like this, very small, through that point, and continues on in both those directions. Okay, sorry, it should look a little more like that. Really hard to draw with these pens. Anyhow, okay, so what's our domain? Well, if you'll notice, the graph goes forever in this direction, but it gets to the y-axis and just goes straight down, more or less. So we know that x then has to be greater than 0, and x is reals, again, because my line is solid. Okay, so any x that is greater than 0 can be used, okay? My range, well, it goes forever downward, okay? And as you notice, as it goes to the right, it gets bigger and bigger, which means y just belongs to reals. The x-intercept, where the graph crosses the x-axis, is here at 1, 0. But because the graph doesn't actually ever touch the y-axis, there is no y-intercept. And behavior goes from Q4, quadrant 4, all the way into quadrant 1. All right, how are these characteristics similar or different to the graphs of exponential functions? Well, remember an exponential function looked like this. Cross the y-axis at 0, 1. Okay, never touch the x-axis. Okay, so the domain was reals, and the range was y is greater than or equal to 0, y belongs to reals, and it went from Q2 to Q1. So how do they compare? Well, look at the domain. Oh, that shouldn't be an equal to, that should just be greater than. Okay, the domain is opposite the range. The range is opposite the domain. The x-intercept is reversed. It's now the y-intercept. Okay, the y-intercept is none, whereas the x-intercept on this graph is none. Okay, so how are they similar or different? Well, they have the same kind of shape. Okay, but that's about as far as it goes. Okay, they are different as the x and y values are reversed. Okay, so what's x on one becomes y on the other, and vice versa. Okay, let's take a look at the natural logarithm. Okay, a base E logarithm. So after working with logs and exponential applications, mathematicians recognized a regular value e occurring. Remember in Chapter 6 on exponential functions, we learned that e is equal to approximately 2.71 blah, 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 blah. It's an irrational number similar to pi. As pi, of course, is 3.14 blah, 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 blah. Okay? So, because this number kept showing up and kept showing up, in regard to natural applications, it is known as the natural logarithm and is represented as y equals log base e of x or y equals ln of x. So if you find e to the x on your calculator, if you press second e to the x, okay, or shift e to the x, or control, I guess, if you're an Inspire owner, okay, then you should be getting ln x, ln, and then you can substitute in the x showing up, okay? Again, I've already put in some scales on here. I guess I didn't do the y-axis. So that is going to be a 1 here, and that's 2, and 3, and so on. Okay, good. So take out your graphing calculator, type in y equals or f of x equals ln of x, and graph it on your calculator. Please pause the video before you do that, and when you come back, we'll graph it up. Okay, so if you'll notice, the graph of this also goes through the point 1, 0, okay? And remember that e is 2.71, so when x is approximately 2.71, y will be 1. And if we square 2.71, we get about 7.4. So there's 7.4, and that's when it's going to be 2. Roughly right there. Again, it comes really close to the y-axis, but doesn't actually touch it. And then, of course, comes out through there. Okay, great. So what do we know about the domain? Well, pretty much the same as y equals 10 to the, log base 10 of x. The domain is x must be greater than 0. X belongs to reals because, again, it gets really close to that y-axis, but never actually touches it. The range, it goes down forever, and again, this continues to increase slightly as x increases. so y just belongs to reals. Okay, the x-intercept also is at 1, 0, and there is no y-intercept because, again, it comes really close but doesn't actually touch it. And behavior is still Q4 to Q1. All right, so what are the similarities? Well, pretty much all the same. So we have same domain, same range, okay, same x-intercepts, same y-intercepts, same end behavior. Okay, so it looks like it's all the same. Okay, slightly different graph just in that it's a little closer to the, or a little further from the x-axis than log base 10 of x is. All right, one example, and then you can get started on page 420. I want you to take out your calculators and graph in y1 log x. Okay, in y2, I want you to graph 5 log x. What happens to the graph? Pause the video while you do that. Okay, as you can see, we have the blue line here, which is log base 10 of x, okay? And then we have the red line, which is 5 log base 10 of x. So what does the 5, because that's the only thing different between these two equations, what does the 5 do to the graph? Well, if you'll notice, it pulls it away from the y-axis, but it also stretches it, pulls it away from the x-axis, okay? So that would be a good thing for you to state there, okay? So the effects on of y equals 5 log x, okay? So that takes, it stretches the graph away from the x-axis. Okay, good. Now what I want you to do is erase those guys. And I want you to instead graph y equals ln x and equals negative, you can just type in 0.5 for a half of ln x. Okay, so all right, so I want you to graph those up. Again, pause the video, take a look at it, and when you come back, I will show you the graph of both of those. All right, taking a look here, here's our graph of the natural logarithm f of x equals ln x, okay? And if you notice then, we have the graph of negative 0.5 ln x. So the negative obviously causes it to flip over the x-axis, okay? So the 0.5, you'll notice that this guy is a little bit further away from the x-axis than this guy. So therefore, the negative causes it to flip over the x-axis, and the 0.5 causes it to get closer to the x-axis. Okay, so let's write that in there. Okay, negative causes a flip over the x-axis, and the 1/2 causes it to get closer to the x-axis. Okay, great. So you get to practice all this and more on page 420. Don't forget to show your teacher when you're done.